U sub, there's a few other things that can happen. There's a lot of other weird stuff that can happen. So you're starting to see, if you were looking at the homework from last night, you're starting to see some of those can be pretty tricky. And then there's a couple of these. What we're going to do today is not real hard. It's just something that I would not typically be doing unless you kind of know it's going to work, or unless nothing else is working. And so, like, based on what we've done so far, if we had this problem, so if I had the integral of x square root x plus 3 dx, it turns out we can use u substitution here. The issue that would have been before is, and still kind of is that the most obvious u substitution would be to let u equal x plus 3. Does that make sense to everybody? And then if you do that, if u is x plus 3, du then is just 1 dx. So we've already got the du. And what, based on what we've been doing, what's the issue with this problem? Like, why maybe is this not
because
something that's, go ahead.
There's an extra x.
Yeah, there's an extra x. And so far we haven't really dealt with that unless it matches what we want. And it turns out that you can't always deal with that, but sometimes you can. And one option is what we're going to end up doing here. So I can solve, based on this equation, I can solve that for x. And so does everybody get that if u is x plus 3, then x would be u minus 3? Does that make sense to everybody? And so if that ends up being something we can handle, so like I can plug the u minus 3 in for this, if that's something we can handle, then it might be something that's useful. So I'm going to go ahead and say, okay, well, I've got the square root of u because u is x plus 3. But instead of x, I'm going to write that as u minus 3 because x is the same thing as u minus 3. And then because dx and du are the same thing, I can just go ahead and replace dx with du. Does that make sense to everybody? Okay, and now what we've got there is not a basic form, but it's something that we can handle algebraically. So if you treat this as u to the 1/2 and distribute it, we're going to have two power functions. So I'm going to take a step to rewrite this. Like that, and then if I distribute it, I get u to the 3/2 minus 3u to the 1/2 du. And we're not done, but does everybody get where I'm getting that? Everybody good? Okay, and so then now what would I do? Why is this going to work even though maybe it wasn't obvious to begin with? What should I do? So I can split it into 2. Does that make sense to everybody? Okay, so I can make this the integral of u to the 3/2 du minus 3 integral u to the 1/2 du. And now both of those are power functions, and there's nothing in the original problem that would have made it clear it was going to end up like this, but it works out. And so now we get 1 over 5/2 u to the 5/2 minus 3 times 1 over 3/2 u to the 3/2 plus c, and then for sure don't leave it like that. 1 over 5/2 is 2/5, and u was x plus 3. And then 3 times 2/3 is 2, and then x plus 3 to the 3/2 plus c, and that's the answer. You could maybe factor something out of there, but there's definitely no need to do that. Questions on what happened there? You guys follow it? Okay. And so that works because when this was like square root of u, if you distribute it, you get two forms you can actually deal with. If this had been, instead of square root of u, if it had been cube root of u or u to the negative third, you can deal with those. If this had been like e to the u or cosine of u, you couldn't deal with them this way, but you could deal with them later. Right now, we could not deal with that. Does that make sense to everybody? Good? Okay. And so let's look at another one like that. Let's say I've got 5x cube root of 2x minus 1 dx. And so again, it ends up being that u substitution works, but it's less of the ones where we know for sure what the form is going to be before we start. But if you look at it and we were going to try u sub, I think the most obvious u sub to attempt would be that u is 2x minus 1. Does that make sense to everybody, that that's at least worth trying? Everybody good? Okay, and if you do that, then du is 2 dx. And so we can get the du at the end of the problem. We've got cube root of u here, and we can get the du. So the issue is that, and the 5 can go out of there. We can factor the 5 out. The x is the problem. So we're going to go ahead and solve this for x. And so I get 2x is u plus 1. And then x is 1/2 u plus 1/2, or u plus 1 over 2. Same thing. Does that make sense? Everybody good? Okay, so I'm going to do a few things in this first step. I'm going to pull the 5 out. I'm going to replace x with 1/2 u plus 1/2. I'm going to then have the cube root of u. And then I'm going to put a 2 with the dx, so a 1/2 outside. Does that make sense? Everybody good? Now, the fact that u is mixed with dx is not ideal because we can't use the rules the normal way, but the point is this part's du. So I'm going to go ahead and take another step to rewrite it like this. And now that's u to the 1/3, and then the 2 dx we're going to replace with du. And now it's going to be a lot like the last problem. But does everybody follow that? Any questions? Okay. And so now I'm going to distribute the u to the 1/3. And now I'm going to split that into two integrals. So I'm going to get 5/2 times 1/2 integral u to the 4/3 du plus 5/2 times 1/2 integral u to the 1/3 du. Questions? Okay, so now we've got 5/4. Oh, there's the chat again. Okay. And so 5/4 and then 1/7/3 u to the 7/3 plus 5/4 times 1/4 u to the 4/3 plus c. And now you flip the 7/3, so you get 15/28. And then u is 2x minus 1, so 2x minus 1 to the 7/3. Now you flip that again, so 15/16. And 2x minus 1 to the 4/3 plus c. And that's the answer. Everybody follow what's going on that? Any questions? All right. Okay. So that works sometimes. It doesn't always work, but it's something worth trying if you can't get a straight up substitution to work like we would have for the past few days. I want to look at one more like that, and then I want to talk about how definite integrals work, but I want to make sure we're good with this. Lots of little places to mess up, so be careful with fractions and stuff. But are we good doing that? All right. All right, so then the other one I want to try is integral of x squared over x plus 7 squared, or to the 7th, sorry. All right, so we're going to try this one. There's other ways to do this maybe later, although I think on this one maybe there's not a good way to do it. But one substitution that might work is to let u equal x plus 7, in which case du is just 1 dx. So we've already got the du. The issue is we've got this x squared that's not really part of anything. So we've got u to the 7th in the bottom, which is fine, but we've got this x squared. Well, based on the fact that u is x plus 7, x is u minus 7. That makes sense? And so then I can rewrite this where I've got u minus 7 squared over u to the 7th du, and I just can go ahead to du because du was 1 dx. Does everybody follow that? Any questions so far? All right, so you can expand u minus 7 squared, and that's u squared minus 14u plus 49. Over u to the 7th du. And now we can split it into 3 fractions. And it's simpler from here, but does everybody follow it to there? Everybody good? All right, so then we've got, I'm going to split it into 3 integrals. So I've got u to the negative 5 du minus 14 integral u to the negative 6 du plus 49 integral u to the negative 7 du. Integral of u to the negative 5 is 1 over negative 4 u to the negative 4. And then minus 14 times 1 over negative 5 u to the negative 5. And plus 49 times 1 over negative 6 u to the negative 6. Plus c, and we're not done. Does everybody follow it to there? Pretty good. All right, so then we can move the u to the bottom and sub it back in. So we get 1 over negative 4 times x plus 7 in the bottom, plus 14 over 5. Oh, I'm sorry, x plus 7 to the 4th. Let's fix that. Doesn't look very neat anyway. All right, so x plus 7 to the 4th, and then 14 over 5, x plus 7 to the 5th in the bottom. And then minus 49 over 6 times x plus 7 to the 6th plus c, and that's the answer. Everybody follow that? All right. Any questions so far? Okay. Okay, and so the next thing I want to talk about is definite integrals that involve u substitution. We'll make sure we're good on this, though. We're all good. All right. Okay, so we're going to move on to this problem. Let's do 0 to 3 x square root . All right, so I want to talk about how to do this. There are two good ways to approach this, and I actually want to go through both methods as far as how to show the notation on this. So you got to be real careful as far as what you're showing. You might be writing stuff that you don't mean and get a right answer, but we do have to be careful with the notation on this. There are two good approaches. And one of the approaches is that when you have these numbers here, as long as this function is continuous from 0 to 3, what the fundamental theorem says is that fundamental theorem of calculus says is that if we can find any antiderivative of this, you then do like f of 3 minus f of 0 and subtract those and you're done. Does that make sense to everybody? Okay, so to me, what makes the most sense is to go off to the side and find an antiderivative of this. So if it were me, the way I would handle this problem is I would come over here and say, okay, I know that I need to find an antiderivative. So I'm going to rewrite the problem without the bounds on it. But I'm going to make it clear I am not saying that this is equal to this. Those two are in no way equal to each other. I'm going to come over to the side and do the work to find the antiderivative. So in this case, I do u equals x squared plus 1. Du then is 2x dx. I don't need to do anything like I was doing up there. I'm going to now move the x to the end of the problem. I'm going to multiply inside by 2 and outside by 1/2. And I get 1/2 integral u to the 1/2 du. Whoops. And then that gets me 1/2 times 1 over 3/2 u to the 3/2 plus c. That gets me 1/3 times x squared plus 1 to the 3/2 plus c. And that's not the answer at all to the problem on the left. But what the fundamental theorem of calculus says is, okay, if you can find an antiderivative, then you can plug in those two bounds and subtract. Well, all this stuff on the right-hand side of the screen is my work in trying to find an antiderivative. And I've found all of them because C could be whatever I want. And so then, okay, the fundamental theorem says, well, then if I found an antiderivative, then I pick one. And so I can pick whatever C value I want. Normally we would pick 0. So you don't put the plus C because we choose for C to be 0. If you want C to be 19, that's fine. You put plus 19 in there. And then you put brackets after or a vertical line after and say, okay, from 0 to 3. And then what that notation means is I'm now going to plug in 3 to the whole thing and plug in 0 to the whole thing and subtract, and now simplify as much as possible. Does that make sense? Everybody clear? Okay, and so 3 squared plus 1 is obviously 10. So you get 1/3 times 10 to the 3 halves minus 1/3 times 1 to the 3 halves. 3 halves power means so like if I'm doing 3 halves power, I take the square root and then I raise it to the third. So like 1 to the 3 halves means the square root of 1 to the third, which ends up being 1. The square root of 10 does not simplify, so I'm going to leave it as 10 to the 3 halves, but then 1 to the 3 halves is just 1. And so that's about as simple as this gets. If I wanted to get a decimal approximation, I could using a calculator, but that's the answer we're going to put on this problem. Does that make sense? Everybody clear? Okay, now that is the way I would recommend doing these problems. You want to compartmentalize and do this basically as 2 separate problems. The work for this first step in the actual problem. So the first step in the actual problem is find an antiderivative and plug them in. The work for that is on the side. Draw a line or something. Make sure you are not saying that this is equal to this over here. It's not. Does that make sense? Okay, do the work on the side, do the antiderivative. That could be real easy. That could be real hard. This one's middle of the road. You do the work over here, and then, okay, the first step is whatever the answer was on the right, and then from A to B, or from 0 to 3 in this case, and then you do this work. Does that make sense? Okay, I think that's the easiest thing to do, but I do want you to understand another way to do it, and we're going to talk about why in a second. So the integral from 0 to 3, we're going to do the same problem, but we're going to show the notation differently. All right, so same exact problem, but there is a way to do the U substitution and deal with the bounds simultaneously where you do it in one problem rather than split it up. And so I want to talk about why I want you to understand this. I think the other way is easier, but let's talk about why it is important to understand what we're going to do here. So we're going to start it the same way, except we're not going to, we're going to start the U sub the same way. We're just not going to separate and not deal with the bounds. So we're going to do U equals x squared plus 1, du is 2x dx. And now with the bound still there, I'm going to start trying to get the du like I normally do. So I'm going to put the x at the end. And now I'm going to multiply inside by 2 and outside by 1/2. And we get it to here. And I want you to look really, really closely at what I'm doing. And don't unmute or don't type an answer, unless you're typing an answer just to me, but not everyone. But I want you to figure out what's weird about that last step and why is it right? Okay, so give me a second, I'll let you answer, James, but let everybody think about it. So look at what's weird about the last step. But why is it not me just screwing up? Why is it right? Okay, so James, I'm gonna let you answer why it's right. Somebody tell me what's weird. What's weird about that last step?
You changed the bounds.
I changed the bounds. So instead of 0 to 3, it's now 1 to 10. Does everybody see that? Okay, so I've got it from 1 to 10. Now, James, why is that? Why is it 1 to 10?
You converted the x units into like terms of u, like u units.
Yeah, exactly right. So, okay, I need everybody to look at the screen very closely for a second. Okay, see the dx here that's in this first problem? Whenever you have a definite integral, that not only means with respect to x, it also tells you that these bounds are x values. Does that make sense? So anytime you write a problem, if you write dx there, those are automatically x's. So this is still dx, those are x's. This is still dx, those are x's. Does that make sense? As soon as you actually change it to du, you no longer get to put x here. These must be u values. Does that make sense? Okay, so if x is 0, u is 0 squared plus 1. So then u is 1. Does that make sense? If x is 3, then u is 3 squared plus 1, which is 10. Is everybody clear where that's coming from? Please ask if not, because I know this is weird. It is very important to understand this, because even if you don't do it this way, which I would not recommend anyway, but if you don't do it this way, you will see books doing it this way. And then in Calc 3, if you're taking multivariable calculus, you end up basically being unable to avoid stuff like this. And so you have to be able to understand this, even though I would not recommend doing it on this problem. And we'll talk about why in a second. But is everybody clear on what happened? Good. Okay, so now we continue the problem. And so I'm going to say, okay, 1/2 integral 1 to 10, and I'm going to go ahead and write it as u to the 1/2 just to make it more clear. And now that's 1/2 times 1/3/2 u to the 3/2 plus c. And now that's 1/3 times, whoops, I'm sorry, not plus c, from 1 to 10. We choose for c to be 0. And now that's 1/3 times u to the 3/2 from 1 to 10. And now we plug in 10, plug in 1, and subtract. Which is then 1/3 times 10 to the 3/2 minus 1/3. And that's the answer. Does that make sense? And it's the same answer, I hope, that we got up here. Yeah. Everybody see that? Okay, so same answer. So both methods work. And like I said, it's important that you understand this method, because basically if you take more advanced math, if you take multivariable calculus, you've got to understand that. You're going to be changing these even more often than we do in Calc 2. And you're going to have bounds that are actually not just numbers. And so you're going to have to be able to convert variables like that. So you want to be able to think this through. And then if you do read a textbook or you look at work online, a lot of them will show it this way. The reason I recommend not doing it this way is because I think it's very, very easy to mess up. So I see people missing problems by using this method a lot more than I do when they're using the other method. And the reason why is because I think down here, what happens is, and me too, you almost instinctively want to go back to x when you're here. Does that make sense? Like I always immediately want to put x squared plus 1 back in here. And if people do that, they forget to make these x's again, and you don't want to do that. These are u's. So if you're doing it this way, once this is an answer in u, you don't go back to x because you change these to u and you plug these in for u. Now, if you can keep track of that, that's completely fine. And this is a legitimate way to do the problem. It's just on a test or something, I think it's very easy to mess that up. Does that make sense? Because I think it's easy for people to forget, first of all, to change to u to begin with. And if you do remember to change to u, it's easy to forget not to change back to x. And so like, if you do it this way, you're going to get the answer right. It's just, there's more room for error in my opinion. And after working with students a ton in Calc 2, I'm actually right about that for most people. Does that make sense? Everybody clear? Now you may be able to do it right. If you want to do it, that's completely fine. You just got to be real, real careful. This up here takes more room, but I like it better, and I think it's better because you're using the fundamental theorem of calculus exactly the way it's supposed to be. So what the fundamental theorem says is find an antiderivative. Well, okay, so I'm going over here and I'm finding my antiderivative, and I'm using whatever method I need. So u sub here, later maybe parts or trig sub or partial fractions or whatever we're going to do. You just do all the work on the side. You get your antiderivative like we always do. And then the first step within the actual problem is, okay, well, this is the antiderivative. and now it's from 0 to 3. And you don't have to mess with changing the numbers or anything like that. Even though this takes a little bit longer, it's a little bit more writing. I think it's easier to keep track of, and it's easier not to mess up. Does that make sense? But you do the way you like. Either way is completely fine. And I definitely want you to understand both ways. Okay? So I do want you to understand both ways. Any questions so far? Everybody good so far? Okay. All right. So I'm going to put one more up, and I want you guys to try it. Let's do the integral from 0 to pi of cosine of x over 2 dx. So I want you to take the time to do it. Try it without a calculator. I'm going to give you maybe 2 or 3 minutes to do it, and then I'll work it here in just a sec. So 133 on my screen, I'm going to give you to 136, and then I will start working it. If you have questions, feel free to text me in the chat or unmute yourself and ask. All right, so I've got a solution on the screen. See if that's what you're getting. And if you're not, let's figure out why I'm wrong or you're wrong. But I think we're good. I think I'm good. Questions on it? Are we getting that? You guys getting 2 as the answer? All right. Good, Colby. All right. So then that's actually it for new material today. So I wanted to go over kind of how to do it when you need to solve for X first, and then how to deal with definite integrals. There is one more homework posted. So it's called homework, more use of and definite integrals. And so there's a bunch of those to practice on WebAssign. That's going to be due Tuesday at 11:59 p.m. as well. So now everything up till now on the course, we should get caught up by Tuesday. If you need help on anything, just go ahead and stick around now. We've got another half hour to work because I'm done talking about stuff for the week. If you do want to meet up tomorrow, I can do that. Just shoot me an email and say, hey, Doug, can we meet up at 12:30 tomorrow? And I'm happy to do that. My schedule is actually pretty full other than that, but I do have the 12:30 to 1:30 or 1:40 hour free. So if you do want to meet up, I'm happy to do that tomorrow. I can also meet tonight at 5. Somebody had emailed and I already set up a meeting with him, but it's somebody from Calc 2. And so anybody who's in Calc 2 is welcome to join that meeting, and we'll just do it on Zoom. So that's 5 o'clock today for sure. And then tomorrow, as long as one or two of you email and want to meet up, I'm happy to do that too. I think I'm going to take off Saturday, Sunday, Monday, take a break. I think you guys should too. Hopefully you're caught up on homework. Try to get this out of the way and enjoy the long weekend. And then we can catch up with whatever you need to on Tuesday. Okay? All right. If you have questions, stick around. If not, I will see you guys Tuesday. Have a great weekend, guys. Enjoy it. See ya.